We are looking down on a surface where there is a disc tied to a rope that's pinned to a table, and also two objects connected to springs that are about to undergo simple harmonic motion. And in normal times, I like to give this animation to my students and encourage them to play around with the speed of the disc and also the spring constants of the spring to see if you can get them synchronized. And eventually everybody does. And once they do, well, it's pleasant to watch. So let's just watch it for a moment. I mean, I'm content to watch this for longer than I should admit. It's kind of hypnotic and soothing. It was in no way obvious or guaranteed that this would be a possible task. Going into this, there's no reason that a person would already know that circular motion could somehow be synchronized with simple harmonic motion, but apparently it can. Now, at some point, everybody finds values that make it work. And then I can ask my students, all right, tell me the angular velocity of the blue disk. So they take the speed and divide it by the radius of the circle. And then find for me square root of k over m for the two objects in simple harmonic motion. And like a miracle, those two things match. The omega that we call square root of k over m for simple harmonic motion is the omega of angular velocity when the circular motion is synchronized with the simple harmonic motion. I'm going to pause this so that I can restart it from the beginning, adding a couple of features. Okay, all I've done is reset the screen, and I've also turned on vector displays so that we can see the velocity and acceleration vectors. And now I'm just going to run this, but just a frame at a time so we can see it unfold slowly. And you can see if we just focus on the vertical motion, the disk and the box are staying aligned, and their vector components match if you just look at the vertical components of the velocity and acceleration vector for the circle. The same thing is true of the horizontal components. Watch the circular disk as it moves horizontally, and the blue box above it that's also oscillating horizontally, and you see they are always lined up with each other. And while their acceleration vectors and velocity vectors don't look the same, if you focus only on the horizontal component, they are the same. In other words, and now I'll let it run, the circular motion can be thought of as a combination of simple harmonic motion in two different directions. Or the simple harmonic motions can each be thought of as the projection of circular motion onto one dimension. And now I'm just going to let it run because it's soothing. All right, I guess we have to stop sometime.